This is my lab report on Physics 2211 Lab 2. So a quick intro to the purpose of the lab. Wanted to analyze the motion of a falling object starting from rest. And in this lab, we get to test the effects of gravity on an object's acceleration, as well as drag force, and then confirm that when there's a net force, the displacement versus time is not linear. And then key concepts. We still see Newton's first law and its effects, where an object will not change its motion unless a net force is applied to it. And we see this in the form of acceleration for the paper ball because of the force of gravity pointing downward. And then we also, like I said, have the gravitational force in this lab. This is the actual equation for the force of gravity, but when we're near Earth's surface, we can approximate this to be negative mg, where g is a gravitational constant of Earth, which is 9.8 meters per second squared. So this is why we see objects accelerate uniformly, at least in ideal conditions, near the Earth's surface. And then the non-ideal conditions, we have drag force, which we will also account for later. More formulas, we have the velocity update formula, which explains mathematically how and why objects accelerate. As you can see, because of this net force term, the final velocity will always be greater in magnitude than the initial, as long as the net force is causing an object to accelerate. And then the system is the paper ball, surroundings, everything else. So the net force on the ball is just everything acting on the ball. And then the net force, it turns out to be a downward net force, which is why it accelerates downward. And then position update explains why the position versus time graph is not linear, because velocity is increasing in magnitude. So for the experiment, the initial conditions, object is at rest, and then it was dropped from a certain height, which I treated as the origin. And then I uploaded the video tracker to measure the change in position, and then created two models in GlowScript, one without drag force and then one that accounted for drag force. This is the tracker demonstration here. So that's the video, and then this is a screenshot of the tracker interface where I tracked the change in position over given time intervals. And then this is the data, which we'll see later. And then this is the code for no drag force, which I mentioned earlier. The main things here are, as you'll see in the next slide, there is no proportionality constant, and that's because there's no drag force. The only thing here is the net force is the negative of the mass times the gravitational constant. And then we also have the velocity update formula and position update formula to create the data at each time interval. And then this is the drag force accounted for model. The key thing was at the top of the code, I added a non-zero value for the proportionality constant here. And then the net force turns out to be the drag force minus the force of gravity, because drag is opposite to the direction of velocity, which is down. So that is a positive y direction force, and then gravity is a negative y direction force. And then here we have the force of gravity is similar to last time. And then the drag force is the proportionality constant times the velocity squared. And then this is the net force. And this is the GlowScript data. As you can see, it's not linear. This is for no drag force. Not linear, similar to actually the tracker data. And then the velocity is constantly increasing in magnitude, decreasing in direction because of the acceleration. And then this is with drag force. As you can see, the model is more leveled off in terms of position versus time, and this is because the forces started to kind of counteract each other. And this is also seen here, and I'll talk about why this is flat at the end. This is the three models compared. This is tracker, this is no drag, and this is with drag. As you can see, this is very flat, which I will talk about in the next slide. So the computation model without drag and tracker actually model similar curves, but the model with the drag has a flat curve, which is likely because it overestimated actual drag force, making it near that of gravity, which suggests minimal drag force on paper ball for duration of motion. Should resemble the model for drag force, but it didn't, so it could be experimental error, which could be error in using tracker or the period of time. And then what does it mean? So on the drag model, the velocity levels off around 0.15 seconds, which is a terminal velocity, which is where the drag force balances gravity, which is constant velocity, so no net force. You can see this here. And then what if the initial velocity was changed? Would terminal velocity be the same? Well, yes. When I change the initial velocity vector in the code to -2, the terminal velocity is reached at a later period of time, but it's around the same value as seen on the previous slide. So changing initial speed only changes when terminal velocity is reached. Thank you.